Next one is a percent yield problem, but it's a little bit backwards. So I want to go over it because it's not the way that we've been doing percent yield problems because they give you different information. So it says hydrogen combines with oxygen to produce water. If the yield for the reaction is 45.0%, how many grams of oxygen will have to be started in the reaction to yield 97.2 grams of water, assuming excess hydrogen? So normally the way the percent yield problems work is that you're given a starting amount of a reactant, and then you calculate the theoretical yield, and then you use the actual over theoretical to get the percent yield, right? But this one, they're actually giving us the percent yield, and they're giving us the actual yield, which they usually do. But the fact that they're giving us this is a little bit backwards. Okay. Algebra to the rescue. So the first thing, though, since we know we're taking a stoichiometry test, what is the first thing we should have? A balanced chemical equation. And this is a nice, easy equation. Hydrogen combines with oxygen to produce water. Okay. Don't forget diatomic. And we need to balance that. So we get 2 here to balance our oxygens. 2 there. Alright, so you should always have a balanced chemical equation, or they'll give it to you. And again, we can label our important parts here. We know that the actual yield is 97.2 grams of water. And we do know the percent yield is 45.0%. There are different reasons that it could be low, but for some reactions, you will have pretty low yield. Yeah. So yeah, when you get answers for, if you're calculating percent yield and you get something that's pretty low, it could be right. Yeah, don't always expect it to be in the 90s. All right, so we know that our formula for percent yield is what goes on the top of a percent yield? Actual yield, right? So we know the actual yield is 97.2 grams. And then what goes on the bottom? Theoretical, which we don't know. Right. But we know the percent yield. And just for simplicity, getting rid of that times 100, I'm just going to set this equal to the decimal version of 45.0%. Just to make it a little bit easier. So we'll put 0.450. So actual over theoretical equals 0.450. Okay. So even though it seems like we are doing this backwards, it's okay because there were 3 variables in this equation, and now we were given 2 of them, so we just have to solve for theoretical. So the magic of algebra, right? If we rearrange this equation, we can solve for the theoretical yields. Right? So having that set up now, we can just solve for our theoretical yield. And remember that this was in grams of water, so whatever we calculate here is going to be grams of H2O. Okay. Right, and we can use 3 sig figs, so 216 is the answer, and that's grams of water. But remember, the question is asking us how many grams of oxygen will have to be started. So we don't have oxygen, but we do have water. So now we are converting grams of water into grams of oxygen. So now we get to use stoichiometry. Yay. hopefully you wouldn't just assume this is the answer, because up to that point, that's water, but also you haven't used any stoichiometry to solve the problem yet. So this part is where we need to use stoichiometry. So now we're doing a mass-to-mass conversion, converting water to oxygen. So mass to mass, everyone's favorite. Need 4 conversions. So it's going to be molar mass, mole ratio, molar mass. Right. What is the molar mass of water? Yes. Those are such nerds now. Okay, so molar mass. Then we need a mole ratio, and we want oxygen. So remember, we get those numbers from our balanced chemical equation. So 1 for oxygen, 2 for water, and then the last one, we would need the molar mass of oxygen, which is 32. Units cancel. Alright, so 216 divided by 18.02 divided by 2 times 32, and we can use 3 sig figs here because of the 216. So we get 192 grams of oxygen. So now we have the actual compound that we wanted. It was asking for grams of oxygen. Now we have grams of oxygen.